Okay, hello everyone. Let's begin. Okay, so well, before we begin, I think all the three assignments are over now, so you should be receiving your grades for the third assignment by next week. So you only have the competition and the exam left. So I think some of you have already started submitting your solutions for the competition. Last time I checked, there were 13 teams who made their submissions, but I encourage all of you to start participating and make sure that like you don't do it, keep it for the last minute, like because you might need to compete with people like who are already in the leaderboard, right? Like so take it sportively and try to get good scores in the competition. And other than that, for the exam, I think I mentioned before that we will be doing the exam on the allotted time. It's going to be an online exam, so it's not a physical exam. And I'll give you a 2 hours worth exam for 3 hours. So the two you are well, like you will be signing a honor code, like and submit it along with the exam, saying that you followed the rules. But the 3 hours is for like it's a 2 hours exam, like, and you have an extra 1 hour to scan your answers and upload it into Gradescope. So maybe we will do a dummy exam probably in a couple of weeks with just 2 questions, like so that you get used to the process. But I highly encourage you to make sure you have good internet connection. You're in a good you're in a comfortable position to sit and write your exam for 3 hours. Like for people who are already in Montreal, like so I know some of you are using the university facility to do that. Like so that's one option. But like I guess you can write it from home. Like it's fine. But yeah, so yeah, we will do a dummy exam. So but make sure that like the dummy exam is there mainly to make sure that you can test your scanning app in your phone, or like the process of uploading to Gradescope, marking the correct question numbers and so on. So if you don't tag the question, you get a 0 for that question. So like practice the instructions in the dummy exam, so that there is no issues when you're doing the final exam. But I can give you more information about the finals, like through email soon. Okay, so let's start. Okay, so in the previous lecture, like we were discussing about different optimization methods, right? So like we started with the simplest one, which is the gradient descent, where the basic idea is like you have theta is equal to theta minus eta, some step size, times the gradient, where j is the cost function, right? Now, then we discussed momentum-based solutions, where the basic idea is to add a momentum term so that you can accelerate the training. So like the basic SGD with momentum would be something like this. You have the momentum term Vt, which is gamma times Vt minus 1 plus eta times the gradient, right? And then the theta is given by theta is equal to theta minus Vt, right? Then we discussed SGD with Nestro's accelerated gradient, which is a smart momentum because like NAG exploits the fact that we are already going to take this step, right? So why don't we look ahead and see what is there in the future so that we can take reasonable steps. So the basic equation for NAG is like Vt is equal to gamma times Vt minus 1 plus eta times the gradient of the model, not at theta, but at theta minus gamma times Vt minus 1, right? You update the model with gamma times Vt minus 1 because we know we are going to do that. Now compute the gradient from this position and then do the gradient descent, right? So that was an SGD with Nestor's accelerated gradient. So then we looked at adaptive gradient methods where like the basic idea is to adapt the learning rate based on the gradients, right? Like the first adaptive gradient method that we looked at was AdaGrad, right? So the basic idea in AdaGrad is like theta t is equal to theta t minus 1, okay, minus eta times, you have the gradient, okay, but you divide the learning rate by summation over p is equal to 1 to t g p square plus epsilon square. Okay, you square all the gradients, you sum them, you take the square root and put that in the denominator. Now the basic idea here is like if you receive large gradients, then the learning rate is going to be reduced because the denominator is increasing. If you reduce, like if you get small gradients, then the learning rate is going to be accordingly increased so that you make faster steps, right? Now we also discussed that there is some problem with this undergrad formulation because this is like a continuous, this is like a complete average of all the entire history. So as time progresses, the learning might saturate. So the simple solution for that was given by RMS prop, right? In the case of RMS prop, theta t is equal to theta t minus 1 minus eta divided by, instead of the square root of summation gp squared, we are just going to do RMS, the root mean square, which is the running average of GT, right? Like, so RMS, if I have to define RMS of GT, was, I don't remember what, like what coefficient I use, rho. Okay, so it's basically, this is basically square. Okay, so to define this, I need E of G square, right? So this is basically rho times E of G square, T minus 1 plus 1 minus rho time GT square. Then the root mean square is given by just square root of E of G square T plus epsilon. So this was RMS prop, right? And then we looked at like the final algorithm, which was Ada delta. And the basic idea in Ada delta was the fact that when you look at the equation, like all the units has to be same. And this led to some slight modification to RMS prop. And the algorithm was basically theta is equal to theta minus eta times. You add an RMS of the updates in the numerator divided by RMS of GT. Right, so this is where we start. So we will just look at one more optimization algorithm, like before we conclude our discussion on optimization, which is the algorithm called ADAM. Okay, so ADAM stands for adaptive moment estimation. Okay, so ADAM estimates the first and second order moments of the gradients and use that to compute the gradient update. Okay, so to compute the first order moment, like, so we are going to do MT, okay, it's ADAM. MT is equal to some beta 1 times MT minus 1 plus 1 minus beta times the gradient. So this is the running average of the gradient. Okay, similarly, we are going to have running average of GT square. We are going to call that as VT. So VT is equal to B2 times VT minus 1 plus 1 minus B2 times GT square. Okay, now this is an estimate of the first moment, which is the mean. Okay, and this is the estimate of the second moment, which is the uncentered variance. Okay, and the beta 1 and beta 2 are some, sorry, this will be beta 1. Beta 1 and beta 2 are some coefficients. Usually the default values for them is like beta 1 is 0.9, beta 2 is 0.99. But these are hyperparameters that you need to tune. Okay. Okay. So now normally when you start training, like you would initialize MT and VT to 0, right? So if you're initializing them to 0, then this process is biased towards 0, especially during the initial steps. So Adam also proposes a way to do this bias correction where you compute the corrected moment as mt divided by 1 minus beta 1t. Okay, similarly, Vt is equal to Vt divided by 1 minus beta 2t. So now you can see that the index, the power, the coefficient here is based on the time. So initially, like you're going to move away from 0 very quickly, and then like you will go back to normal. So after 100 steps, the denominator is going to be almost close to 1. Okay. Now the gradient update is given by theta t plus 1 is equal to theta t minus eta divided by Vt plus epsilon, and you have mt here. Okay. Now, if you look at how this Adam update looks like, now this part is very much like RMS prop, right? And this part is very much like the momentum term, right? So in some sense, Adam is basically combining RMS prop and momentum. Okay, and Adam is actually probably the most popular optimization algorithm. Like, so if you're using package, like if you're using even in sklearn, like I think the default optimizer for neural networks is Adam. Like in a lot of packages like Keras and other like neural network packages that you would use, like you would see Adam to be the default optimizer. But there is this question like which is the right optimizer to use for, right? Like so, like should I have listed at least one, two, three. I have written at least 7 or 8 optimization algorithms, right? Like so, the default optimizer that people often use is Adam, but I would like to remind you that like there is no single best optimizer like which would work for all the tasks that we have. Okay, so in some sense, you should treat the optimizer as the hyperparameter. Like you should try Adam, you should try SGD, you should try SGD with momentum and so on. So like I would suggest, like if you have to try few optimizers to begin with, you should always try Adam and SGD with momentum. So then you could try other things based on your computation, on the available computation and time. Okay. But there is a lot of research in the optimization community on which optimizer is better in what situations. And there are even some questions about, there are some claims that SGD is better in generalization when compared to Adam and so on. So we don't have a clear like universal optimizer. So you have to try quite a few optimizers like if you want to improve your performance. Okay, so some final notes before we conclude this topic. So additional strategies. So when you do gradient descent, especially mini-batch gradient descent, you should always shuffle your data before every epoch. Okay, and it is better like if you always try to use batch norm or like we discussed batch norm, there are like other normalization techniques available like layer norm, or like there are a lot of normalization techniques. So you should try to use one of these normalization techniques because it's going to make the optimization easier. And you should always do early stopping. Okay, so what is early stopping? So you basically stop training when the validation error did not improve for some time. For example, you could say that for every 5 epoch, like you could check for 5 epochs. If your validation error is not at all improving for 5 epochs, then like you stop. So that is early stopping. Okay. And another trick that people normally follow is like whenever your validation error, let's say, is saturated, you could reduce the learning rate at that point. You divide the learning rate by 2, then you might see that you will start learning again. So like when you're saturating, it might be the case that you are like in a very complicated, like you're in a very narrow ravine that like you need to like reduce your learning rate so that you take smaller steps. Okay, so sometimes adding noise to the gradient helps to escape local minimum. Okay. However, if you are doing gradient noise, then you need to be careful. You cannot keep adding noise throughout the training. You should anneal the noise. Anneal the variance of the noise slowly, so that after some part in the training, like you stop the noise. Okay, so that concludes our discussion on optimization. Any questions before we move on? Any questions? No, for your competition, you could actually try different optimizers with the models that you're training. Any questions in chat or hand raise? Okay, it's surprising that there's no question. Okay, so let's continue. So for today's lecture, we are going to look at a very specific type of neural network architecture, which is called convolutional network. Okay, so now when you normally use a regular neural network, okay, it takes a single vector as input, right? On the other hand, like when you are using some specific types of data, like it might not be a vector, right? Like, so to give you an example, let's say I have images. Okay, now here is an example data set. So this is called CFAR10 data set, where the 10 stands for 10 classes. Okay, so in this case, I have 10 classes: airplane, bird, cat, dog, and so on, right? And we have images for these 10 classes. Now, each of these image is represented by pixels, right? So now in this case, specifically, we have 32 cross 32 cross 3 image size. Okay, so this is the pixel information. So now 33, like this 32, the first 32 is the height of the image. You have 32 rows in the pixels. And this 32 is the width of the image. And 3 stands for the color channels. Okay, so you have RGB, right? So now this is a structured data, right? Like, so you have a tensor of 32 cross 32 cross 3. Now, if you want to use a regular neural network to solve this problem, okay, now how would you give this as input to the neural network? Any answers? I want to give this matrix or tensor as input to a regular neural network. Yeah, so one answer is you flatten it to 1D, right? Like, so you just, you flatten this out, and then you are going to get 32 cross 32 cross 3, which is 3072. Okay, so you would have a 3072 dimensional vector, the flattened vector, and you will pass that as input to the next layer, and you might have many layers, and finally you have a 10 unit output, right? Now, look at this first unit in the first hidden layer. Now, this unit has to be connected with all the units in the input, right? So now this one specific unit is going to require 3072 weights. Is that right? Okay. Now, here's the issue. So this is fine for a 32 cross 32 image. Like I flattened it and I gave this as input. Maybe some of you have already tried this in your computation. But imagine I have a 200 cross 200 cross 3 image. Okay, so this is very common. Like nowadays we even have 1024 cross 1024 or like 4096 or 4096 pixels, right? So 32, like 200 is still a small number. Okay, so even for this small 200 cross 200 cross 3 like image, like you would require 120,000 weights just for one unit. Okay, if you have 100 units in this layer, then you require 120k multiplied by 10 weights in the first W1 matrix. Okay. Okay, so there's a question in the chat. Does the order matter? Can we compare this with the end layer? No, the order doesn't matter when you're flattening out. Okay, so now that is also a good point. So we'll come to that. Okay, now this is a lot of parameters, right? So a lot of parameters. Now imagine, to give you some example, this C for 10 data set has only 50,000 examples. You have 50,000 examples, and even for a single unit, you need 120,000 weights in the first layer. Okay, so now this would definitely lead to overfitting. Now, this is not the only problem. The second problem is something that Masood pointed out, right? Like, so when you flatten the image, you actually lose the structure, right? So in a fully character layer, it doesn't matter like whether like you have one permutation of this structure or not, right? Like, so it is a set, like it's not like a sequence, right? Like, so this is also another problem. Like image actually, on the other hand, like if you look at the image, like for example, if you just go to one of these images, like here, like in this horse image, you can actually see that horse is defined by a group of pixels which are nearby each other, right? Like, so you need to look at all these pixels together. Like if I'm going to shuffle all the pixels in this image and give it to you, it's going to be a harder problem, right? Like imagine I shuffle this completely, you have the eyes of the horse in one corner, like another part in the other corner and so on. So in this case, like it's going to be a very like hard problem to solve. So the structure matters, and a fully connected neural network cannot handle this. Okay, so now this brings us to a very special type of architecture for handling images, which is convolutional networks or convolutional neural networks. Okay, so you could call them as CNNs or ConNets. Okay, so what are ConNets? So ConNets are basically neural network architectures which takes advantage of the structure in the image. Okay, now in the case of a ConNet, the neurons are going to be arranged in 3 dimensions. Okay, so we are going to call them as width, height, and depth. Okay, now each conv layer, right? So a conv layer, okay, it takes a 3D volume as input and it actually produces a 3D volume as output. Okay, now remember that in the case of a regular neural network, it takes a vector as input and it produces a vector as output, right? Like on the other hand, coordinates take a 3D volume as input and 3D volume as output. So to compare neural networks, regular neural networks with coordinates, you can see here that in the left side, I have the regular neural network. Like, so you have a vector as input, and this layer takes this vector and produces another vector, which is given to the next layer and so on, right? So this is a regular neural network. But in the case of ConvNet, you take a 3D volume as input, and this ConvNet is passing it to another 3D volume, another 3D volume, and finally you have a 3D volume of 1 cross 1 cross 10, which is corresponding to the probability for the 10 classes. Okay. Now each 3D volume has its own height, depth, and width. Okay. Now this is the basic idea. Okay, so the basic idea here is to exploit the structure of the image, like so that we can do better than regular neural networks. Okay, now what, like, and I just told you as a black box, there is this con layer, right? Like, so now what types of layers we can use in a convnet? Okay, so the fundamental type of layer that we are going to use is the convolution layer. Okay, and we will also discuss another type of layer called the pooling layer. Okay, and finally, towards the end of the network, you will have the fully connected layer as usual, because that is what is going to give you the probability of the classes. Okay, now let's start with convolutional layer. Okay, so now the conv layer is going to have some parameters. Okay, now these parameters of the conv layer are some learnable filters. Now, what is a filter? So every filter in a convnet is some spatially like assigned object. Okay, so for example, like I could have a 3 cross 3 cross, maybe to make things. Remember that I have a 32 cross 32 cross 3 image, right? Now one pixel could be like one filter could be 5 cross 5 cross 3. Okay, so now once you have this image, now this small 5 cross 5 cross 3 pixel is the filter. Now I'm going to put this filter over every region of the image and use this to compute an output. Okay, now let me show you a quick animation. Probably that would make it easy to understand what is happening here. Okay, let me see. Okay, so here is a okay. So maybe I need to optimize this for picture. Okay, so, well, I think I'm not sure if it is clear enough. Is it clear enough? Can someone comment? Okay, for some reason, I don't see it clearly, but anyway, I think this serves the purpose. So now in this case, you see the image, which is represented in the first column. Okay, so it's a 7 cross 7 cross 3 image. Now, which means that there are 3 7 cross 7 matrices. Okay, and you see the filters like W0 and W1. So W0 filter is 3 cross 3 cross 3. Now you take this 3 cross 3 cross 3 vector, and you can see that as the animation moves, like you are looking at one particular patch of the image, you compute the dot product, and that is what is going to be the output. Okay, and you continue this. So Is this clear? Okay, it's a bit blurry. Okay. Okay, but I think the numbers doesn't matter. Like what matters is like how the operation is done. Okay, so moving back to our discussion. So basically, like we have this concept of filters, and we are going to use these filters in the forward pass to do a dot product with parts of the region. Okay, so now this one specific filter, when it moves through all the parts of the image, it's going to create a 2D map, right? Similarly, I could have many filters. Now each filter is going to produce a 2D map. Okay, so now maybe let me explain this better. So now, if you remember, in the case of regular neural network, you have your input unit, input layer, right? So now this is a vector. Now you had these neural units in the hidden layer, right? Now each of these units was connected to all the previous units, right? And you would use that to continue with the neural network, like whatever number of layers you want. But in the case of convnets, we are going to start with an image. Okay, now this image is going to have, let's say, 28 cross 28 cross 3. So there are 3 channels: R channel, G channel, and B channel. Okay, each channel is 28 cross 28. Okay, now the conv layer is going to have a bunch of filters. Instead of having those neuron units, they are going to have these filters. Okay, now each filter is going to look at one specific region. Okay, and use that to actually produce. So this entry is produced by looking at this region. Okay, now I can use a different color to show, like you look at this region. Okay, and that is going to be used to produce this part. Okay, so now if you just move left to right throughout the image, you will fill this entry. Now this whole thing is done by one filter. Now similarly, I can have the second filter, the third filter, like I could have, let's say, K filters. Okay, right? So now you see that this conv layer actually takes a 3D volume as input, and it produces a 3D volume as output. Now I can have the next conv layer, which is going to take this 3D volume as input and produces the next 3D volume as output. Okay. Now there is a fundamental difference between a feed-forward network and a conv network, right? Like, so here you can see that this filter is actually not connected to the entire image. Okay, so it is not connected to 28 cross 28 cross 3. Instead, it is only connected to, let's say, 5 cross 5 cross 3, and this is repeated. Okay, so there are two major things that you should understand here. Like, one is the idea of local connectivity. So you are locally looking at parts of the image. Okay, second is the idea of parameter sharing. So using the same filter to go through the entire image. So in some sense, you are sharing the parameter like across the image. Okay, so now if you have a 32 cross 32 cross 3 image, okay, and if you have a filter whose receptive field, so the receptive field is basically how much the filter can look at. Let's say it's 5 cross 5. Okay, so then essentially you only have 5 cross 5 cross 3, which is just 75 weights, plus like you have one bias, right? So okay, so remember that the depth must be 3 for this filter, because this filter has to look through all the 3 channels, RGB channels. Okay, now this is much smaller than having a regular feed-forward network, which will have 32 cross 32 cross 3 parameters. Okay, is that clear? Like we are going to get into the details of how I just gave you a like an abstract overview of like a conv layer. We are going to look at like exactly like how this is going to work. But before that, any questions? So there are a couple of questions here. If the input and filter size is fixed, does that also fix the output size? That's a good question. So that is what we are going to look at right now. So like if I have a specific type of input, like 32 cross 32 cross 3, and if I have a specific filter size, let's say 5 cross 5 cross 3, then that is going to give you a fixed output. So we will see how to compute that output size soon. Is connected to region of the image. So yes, well, I'm not sure how to interpret Mohammed's question. Like, I think if the question is this architecture is capable of looking at the regions in the image, yes, this can look at regions when a regular feed-forward network cannot look at the regions. How to train such a layer? That's a very good question. So that is what we are going to look at now. But is the general idea clear? Okay, so there is okay, so from if our input is not 3D, using CNN is logical or not? So that is also a good question. So you could you could use CNNs with even 1D or any dimensional input. So, but probably we will not touch that in this course. For today's lecture, like we would just focus on images. So how to choose a filter? Are there many layers? Okay. Are there many filters per conv layer? Yes. So we are going to, as I shown here, you could have k number of filters. The number of filters is a hyperparameter. But how to choose? I think by how to choose, you mean how to learn these filters. That is what we are going to look at right now. Okay. So now let's actually get into the technical details. Like now that you have a rough idea of like what is a conv doing. Okay. Now, how can we design such a filter, right? So to do that, there are actually 3 hyperparameters. Okay. Now, the first hyperparameter is the depth. Okay. So now depth of the out. Okay. So what would be the depth of my output? Okay. Depth of my output actually corresponds to the number of filters I use. Number of filters I use. Okay, so for example, in this case, if I use k filters, then I will produce k 2D maps. So what is the height and width of this 2D map? We are going to find it now, but we already know the depth of this 2D map. The depth of this 2D map is exactly k, because you're going to have k such maps, right? So the depth is decided by the number of filters we use. Okay, now there is a second thing which is called stride. Okay, so what is stride? So when the stride is 1, okay, so we move the pixel 1 pixel, we move the filter 1 pixel at a time. So we move the filter 1 pixel at a time. So let me give you an example. So let's say, just for simplicity, 1 2 3 4, okay, do we have 6? Okay, 3 4 5. So this is a 6 cross 6 image. Okay. And let's say I have a 2 cross 2 filter. I have a 2 cross 2 filter. Okay. So what I would do is I would take this 2 cross 2 matrix and I would do a dot product with this 2 cross 2. That is going to produce the first output. Okay. Now, if my stride is equal to 1, I would just move my window to by one step. Okay, so I would do this. Now this is entered here. Okay, so then I would move one more step like this, and that will be entered here. One more step like this, that will be entered here. One more step like this, that will be entered here. Okay, so now you can see that the width here is actually 6, but after doing this convolutional layer, I got a width of 5. There is some reduction happening, right? Now this is with stride is equal to 1. Now let's do the same thing, but with stride is equal to 2. Okay, maybe I should have copy pasted the filter. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay. If I do stride is equal to 2, then I will compute this entry. I'm going to put it here. Then instead of skipping 1, I'm going to skip 2. So I will do this. And I will have the second entry. Then I will skip 2 pixels. So I will do this one. Then I'll get the third entry. So now you can see that this output was of size 5, but this output is going to be of size 3. Okay. So now this is the stride hyperparameter. So you decide the stride hyperparameter. You could play with this hyperparameter to decide what is the output that you want. Okay. So finally, there is a third hyperparameter, which is zero padding. Okay. So sometimes it is actually convenient to zero pad your image. Okay. So let's say this is my image. Okay. Sometimes it is actually convenient to add a layer, like one layer or two layers of just zeros. Okay. Now, can someone tell me why do I need, like, what are the situations in which I need, like, I would add, I would make the image bigger by adding zeros? Okay. So there is one question, which is like one answer, which is to fit the filter. Yeah. Sometimes your filter might go out of the border. So to fit the filter, any other reasons? That's a good answer. So it's for fitting the filter. Any other reason? Okay, that's a good answer. So if you actually want, like we saw that based on the strides, you actually get smaller images, right? Now, if you want to keep maintaining the height and width of the image as you progress in the layers, then you have to zero pad accordingly. Okay. Okay. So now we have seen a bunch of hyperparameters, right? Like the first one is the receptive field size. Okay, what is receptive field size? It is the size of the filter, 3 cross 3 and so on. Then you have stride, let's call that as yes. Then you have zero padding. Okay, so amount of zero padding. So if I say P is equal to 1, then I do one layer of zero padding. If I say P is equal to 2, I do two layers of zero padding. Okay, now W is basically the input volume size. Okay, now the output volume size, there is actually a formula to compute the output. Like you can easily compute what would be the output size of the image. Okay, that is given by W minus F plus 2P by S plus 1. Okay, let's take an example. So for example, if I have a 7 cross 7 input and a 3 cross 3 filter and a stride of 1, and there is no zero padding. Okay, now what would be my output volume? My output volume is going to be 7 minus 3 plus 0 divided by 1 plus 1. So this is going to be 5. Okay. Now, similarly, if I just do a stride of 2, instead of stride of 1, I'm going to do stride of 2. So then this becomes 7 minus 3 by 2 plus 1, which is 3. So you can see that the output is going to vary based on how I change the stride. Okay, so I have a 1D example. So someone asked me if this can be done only for 2D, right? So you like 3D, right? So you could do it for any number of dimensions. So here is a 1D example. So in this case, so this is my filter. Okay, so this is my filter. So this is actually a filter f is equal to 3. Okay, so now this is my input. The width of the input is 5. I have 0 padded with just 1 0. So the padding is equal to 1. Okay, so now you can see that first I will do a dot product of 0, 1, 2 with this one, and that is going to be this value, right? If I have stride is equal to 1, then I will do this to produce this. And let me see if I can change the colors and it works. And I will do this to do this, and so on, right? So now this results in a 5-dimensional output. You can see that because of the 0 padding, my output is exactly 5 dimensions now again. Okay, now if I do stride is equal to 2, you can see that this becomes minus 2. Then it's a stride of 2. So I skip 2 and I go to here. This results in this, and so on. So now you can see that the output is only 3. Okay, so now just to remind you why we use strides, why 0 padding. So 1, you could use it to keep same size. Okay, 2, you could use it whenever you have constraints on strides. Let me give you an example. For example, in the previous example that we had, right? Like, so in this example, like what if I put stride is equal to 3? Okay, so can someone tell me what would be like, can someone tell me like, if I can do stride is equal to 3 here, so what would happen? So this is one entry, right? Then the second entry is going to be this, right? Now this is left out. So I cannot do convolution properly. So when s is equal to 3, I get 5 minus 3 plus 2 by 3 plus 1. So this is 4 by 3 plus 1. So this is not an integer. Okay. However, I can make it work by just adding one extra 0 here and here. Okay. So if I put p is equal to 2, then this becomes 5 minus 3 plus 4 by 3 plus 1. This is 6 by 3 plus 1, which is 4. Okay. So is this clear? Now, someone asked, how do I learn the filters, right? So now you can see from here that this is the parameter of the filter. So this filter has 3 parameters. So just like how you do backpropagation through a regular neural network, you can also do backpropagation through this convolutional neural network. Okay, I did not write the equation of this layer, but you can write the equation and you can differentiate it and you can compute gradients and you can actually learn this parameters. Okay, so I think we are running out of time. So, well, I just introduced the conv layers, but we are going to probably discuss a bit more about convolutional networks in the next lecture. Any questions? So I can see some questions in the chat. What's the depth on? Oh, okay. So we don't have depth in this example. It's a one-dimensional example, right? So if you have an image of RGB channels, then your depth is 3. Is that clear, Jonathan? Okay. There's a question regarding slide or stride. So, oh, no, you decide the stride. So if you cannot say there is no stride, you have to have at least a minimum of stride is equal to 1. Because stride tells you how you move through the image. Okay, any other questions? Okay, so okay, there's another question. Does the stride apply only horizontally? Okay, so if you go to the image, so you do the stride horizontally, but then you go back. It's like scanning every row. So then you go back to you go to the next. Okay, so now this is a good question actually. So if I have a stride of 1, when I go to the next layer, I would actually do this. Okay, but if I have a stride of 2, then I would go down two rows. So you will do it across the entire image. Okay, can using filters result in decreasing the accuracy of the model? No, in fact, it actually helps you. So we will discuss more about that in the next lecture. So these filters are in some sense, okay, now you already see how these filters are functioning, right? Like, so they look at a part of the image, right? Like, so now if I go back to my image example here, like, so if we zoom into this, so for example, like I could have one, okay, let's take this dog, okay? So I could have like one filter which is responsible for the nose of the dog. Okay, it will just look at where the nose of the dog exists. So it will check here, okay, there's no nose, check here, check here, check here. It will continue checking and it will see that here there is actually something which looks like nose of the dog. Similarly, you could have another filter which will learn to just look for the tail of the dog. So these filters are actually much more powerful. So they are going to help you in increasing the accuracy because they will learn the meaningful features or subparts of the image, which are useful for classifying. Okay, is there any other questions before I stop the recording? I'm sorry. Okay, oh, by the way, so the self-assessment section has been updated up to like today's lecture. So you have the questions for all the lectures so far. So it might be useful for your preparation for the exam. Like, so like after you read every chapter, like that will test whether you have understood the concept from the chapter. Okay, so if there are no more questions, then I think I will stop the recording.